Welcome to Arc Dev Labs. It's good to see you.
Imagine a stadium packed with 713 million people, all shouting a different song request at the exact same time. Serving that massive audience requires hosting 100 petabytes of audio across a sprawling physical footprint of global data centers. Today, we are stepping behind the curtain to tear down the engineering architecture that keeps this massive operation running. Pushing continuous audio to hundreds of millions of simultaneous users means traditional single-block application architecture simply collapses under the load. Running a live show of this scale requires completely independent crews. One team handles the lighting, another mixes the sound, and a third manages security. Software architecture mirrors this. A monolithic codebase breaks apart into decoupled microservices. A user service handles logins. A playlist service owns track sequencing. If the search service crashes from a query spike, the other blocks keep streaming uninterrupted. To manage this fleet, engineers use Docker to containerize these individual services, while Kubernetes acts as the orchestrator, instantly spinning up thousands of new server instances the moment an artist drops a surprise album. By severing the dependencies between features, a localized failure is physically isolated. The entire platform cannot crash at once. A flawless DJ set relies on crossfading, queuing up the next track before the current one finishes so the beat never stops. Instead of downloading an entire 7-megabyte song, the file is sliced into chunks. The client begins playback immediately. If the signal degrades, the client automatically requests the next sequence as a smaller, lower-quality chunk, absorbing the network drop without pausing. To minimize the physical distance these chunks have to travel, identical copies of the catalog are preloaded onto Content Delivery Network edge servers stationed in major cities worldwide. Client-side pre-buffering paired with localized edge nodes effectively masks the instability of the open internet. The listener hears continuous audio, entirely unaware of the data drops happening behind the scenes. A massive mixing board routes hundreds of live instrument feeds to different speakers and monitors simultaneously. In a distributed system, that routing is handled by Apache Kafka. It serves as the event-driven backbone of the entire architecture. Every play, skip, pause, and playlist addition is logged as a discrete event. Kafka captures these billions of daily actions, categorizing them into distinct topics. Independent downstream consumers then pull from these topics at their own pace. The analytics engine processes listening history, while the royalty system calculates artist payouts based on those exact same play events. Because Kafka decouples the producer of the data from the consumer, heavy back-end processing can run indefinitely without ever blocking a user's ability to skip a track. Maintaining a rapidly updating, globally accessible record of hundreds of millions of active users requires an impossibly massive filing system. Engineers solve this with polyglot persistence. Rather than forcing all data into a single database, different services utilize the storage structure best suited for their specific access patterns. Relational databases, like PostgreSQL, are deployed for tasks demanding strict data consistency, like verifying complex, region-specific licensing rights before a track plays. But strict consistency has a fatal flaw. In 2015, a broken transatlantic cable severed the link between European and American data centers. The legacy relational databases struggled to synchronize across the damaged network. The resulting latency exposed the inability of a central relational model to handle massive, distributed metadata loads. The solution was Apache Cassandra. As a NoSQL database, it sacrifices immediate consistency for extreme availability and horizontal scaling, handling highly intensive read and write loads across multiple regions. To migrate millions of user profiles from Postgres to Cassandra without taking the app offline, engineers used dark loading, duplicating live user traffic to both databases simultaneously until the new system was proven stable. Polyglot persistence ensures that the strict legal compliance required for music licensing and the infinite scale required for user metadata operate independently, preventing one from bottlenecking the other. A great DJ reads the room to predict the next track. A global streaming platform has to read the preferences of hundreds of millions of individuals simultaneously. When a user looks for a track, an Illusearch cluster scans an inverted index of 100 million songs, employing fuzzy matching to correct typos and return results in under 50 milliseconds. Once the track is playing, a hybrid machine learning engine takes over to generate the next personalized recommendation. The first layer is collaborative filtering. The system identifies users with highly similar listening histories and cross-recommends tracks between their overlapping profiles. This diagram shows the second layer, content-based audio analysis. It plots a multidimensional embedding space where raw audio files are mathematically mapped based on acoustic traits like tempo, energy, and valence. Real-time event streams from Apache Kafka continuously feed user skips and replays back into these models, adapting a listener's daily mix on the fly. By pairing behavioral tracking with the mathematical analysis of raw sound waves, the system successfully categorizes and recommends brand new uploads that have zero existing play data. A conductor ensures the brass and strings strike the same chord at the exact same millisecond. Traditional HTTP request-response loops, where a client repeatedly asks a server if the state has changed, are simply too slow and resource-heavy to keep a desktop, smartphone, and smart speaker perfectly synced. Instead, the architecture establishes persistent WebSockets. These open bidirectional connections allow the server to push state updates instantly to all active devices. This is managed through a leader-follower model. The device currently controlling playback acts as the leader, sending a pause command to the server, which immediately propagates that command to all follower devices. If a user picks up their phone to change the track while the desktop is playing, the server executes an atomic lock, instantly transferring leadership status to the phone and overriding any conflicting commands. Maintaining exact sub-second state agreement across volatile networks and disparate hardware makes multi-device synchronization a significantly harder distributed systems problem than streaming the audio itself. After a massive festival, the cleanup crew has to sift through millions of discarded ticket stubs and receipts to tally the final numbers. Each year, billions of individual listening events are tallied into a massive annual data flow job, culminating in a highly publicized, personalized summary. To process this astronomical volume of historical records, engineers write data processing pipelines in SIO, executing them through Apache Beam. The efficiency of this operation relies on the sort-merge bucket format. It aggressively partitions and shards the data across the Cassandra database, allowing hundreds of nodes to process segments of the user base in parallel. Massive parallel batch processing takes cold, dormant infrastructure logs and computes them into an interactive cultural event. Delivering an intimate, personalized listening experience to a single user requires an unimaginably complex, globally distributed machine running flawlessly behind the scenes. It requires decentralized microservices, localized edge networks, real-time event routing through Kafka, the relentless horizontal scaling of Cassandra. The next time you press play, you are commanding a global symphony of servers.